Welcome to lecture 23. So in this lecture, we will discuss uh, some open source and commercial real-time operating systems. So these are of course old and classic designs, mainly of the late 90s and early 2000s. But many of these concepts have also come into state-of-the-art real-time operating systems. So there is a list at the end of this lecture. But the main aim here is to look at older designs and look at their uh, design principles. So the principles always remain the same. So starting from the last lecture, we did discuss the POSIX standard and the different application environment profiles that are a part of the POSIX standard. So real-time operating systems, at least as of today, are very important because automobiles, self-driving systems, all kinds of IoT systems are big consumers of real-time operating systems. So we have the VDX for automobiles, Symbian, Android, etc. You know, iOS. So these are all well, even though these are general purpose mobile phone operating systems, but they do have real time characters in the sense phone or video, etc. are real time applications, right? They have real time requirements associated with them, and this is why it is important to look at them at least as soft real time operating systems. And there are different standards, of course, that are used in different parts of the world: Japan, Europe, US, and so on. So, several efforts in this direction have happened in the direction of extending Unix and Unix like operating systems to support real time features. So, one of the key ideas is implementing real time task schedulers. So, here the idea is that we have a new class of schedulable jobs and a new scheduler which implements EDF or RMS based scheduling. Definitely work on the timers, so have more finer granularity timers, real time file systems, and storage. But the issue is given the fact that the underlying substrate or the underlying operating system as such is non real time, these additions do not provide a great amount of real timeness to the operating system, right? At best, they provide some features, a minor degree of relief. But the major problems still remain, which are as follows. So, two major problems remain, and the two major problems are like this: that tasks or large parts of the kernel are not preemptible. So, the lack of preemptibility is an issue. And definitely, interrupt handlers and even storage and IO, they are not real time ready, right? So, basically, interrupts, storage, and IO are not real time ready. So that is why there are a bunch of approaches to make Unix more suitable. So one is, of course, we modify the kernel or modify large parts of it to bring in these two features. The other is a host target approach where what we do is we develop the the system is developed on the Unix machine and then it is transferred to the target, the real time target. Then we'll discuss self-hosting systems and preemption points, and then a fully preemptable kernel. If not fully preemptable, let's say preemptable to a very large extent. So we have already discussed extensions to Unix. So the next is the host target approach. Here the idea is that you develop an application on a Unix host and then the application is downloaded to a dedicated OS, which is most likely a non-Unix OS, right? So why is this done? Well, the reason it is done is because all the development tools will be there on the Unix host and the dedicated OS will be much smaller. That will be running on the target. The host will be connected to the target using a networking interface, a TCP IP interface. So some examples of this category would be, the popular uh, operating systems from Wind River systems, and in fact many more, such as embedded Linux, MC Linux, and so on. So what happens is that these nodes are so small and feeble that they cannot support or host a full-fledged development environment. That is why the Unix host, the Linux host, will have the full development environment along with a virtual CPU if the CPU is different, which in most cases it actually is, where you can design, develop, debug, and test the entire application on the host first before actually transferring it to the target. So this is what the host target approach would look like, where the applications are designed on the host and then they are transferred to the target. So the target operating system is intended to be compact and fast. So it is suitable for embedded applications. It need not support the full fledged development environment, which in this case would comprise the compilation, debugging libraries, virtual memory, etc. And the task preemption time, particularly in that on the target, right, is expected to be very small, expected to be of the order of 10 microseconds, whereas actually it is much more on a traditional operating system. And again, there are a lot of reasons for that. Uh, but the key point is that it can be as high as 10 to 100 milliseconds on a Unix application. So coming to the host and target idea once again, what we see, so again, this is an example of the PSOS operating system, an old operating system, but let's look at the idea. So on the host, we have the full development environment, which comprises the entire development compilation toolchain, the libraries. And once the application is developed, it is transferred to the target, where the, of course, the application runs, along with dedicated PSOS libraries. And often what is supported on such systems is known as a target debugger. So the idea is that since we don't have a full, development environment, you don't want to support a full debugging system, but at least there should be some way of finding out what exactly the application is doing, and in case it has crashed, where it has crashed. That is why what happens these days is that we can attach a USB based debugger back to the host, which will be giving some information about the executing application to the host, such that the host can make a decision, right? And such that the host can get some debugging information. So PSOS, the host would provide the following development tools. So the most important being the cross compiler. What a cross compiler does is that you compile it on the host, but the code that is generated is for the target. Then of course we'll have libraries for the target, editor, other development tools, and in if you would have seen the last slide, the X-ray plus module at the middle was the source level cross debugger. So along with a cross compiler, we need a cross debugger where basically on the host itself we are simulating the target and we are also debugging the application on the target. Everything happens on the host. Once we are sure that the application will execute correctly, it is transferred to the target. So the application, as I said, is developed, debugged on the host. Once it is fully tested and debugged, either it is transferred to the target via the network via USB port, or what used to happen in the older days is that the entire code was fused in a read-only memory, a ROM, and the read-only memory itself was transferred because the instructions don't change. So PSOS, of course, what I am describing now is an old idea, but the idea is old, but the concepts are fundamental. So a little bit of history. So Wind River Systems has been a very iconic company in the development of real-time systems. Uh, the development as of now has been halted. So of course, Wind River was acquired by VxWorks and so on. So uh, I'm sorry, there was some degree of convergence with VxWorks, but there are a bunch of projects, a lot of real-time projects that have drawn a lot of inspiration from these early designs. Another project which is very popular, it still exists though as of today, as of 2022. So it supports PSOS plus its APIs, and it allows existing real-time industrial applications to migrate to a GNU Linux-based environment. So XenoMi is essentially is a layer on Linux for allowing real-time execution. Now we'll come to preemption points, right? So preemption points are essentially points that are introduced in system calls. So basically, this is where essentially the kernel can be preempted. All right. So at these points, it is guaranteed that the kernel data structures are not inconsistent. So that is why we can preempt. So basically, what happens is that instead of making the kernel preemptible at every point, we have fixed preemption points at which a preemption is possible. So at these points, the operating system will look for other tasks to run. For example, system services, subsystems, interrupts, and so on. It can either run them, right? So this will give the kernel a better response time. Or what it can do is that it can schedule other real-time tasks, right? So some examples of large operating systems that support preemption points are HP, Unix, Linux, and so on. So this is taking us to the idea of a fully preemptable kernel where the entire kernel, like a user application, can be preempted at any point. So for this, the main thing you need to ensure is that the kernel data structures are always consistent. So for this, we can use locks in the sense we can have kernel level locks. So once acquired, nothing in the kernel can acquire that lock once again. But the main thing is that you can take the lock and you can go to sleep. So other is fine-grained spin locks, where if let's say one kernel thread has acquired a lock or one process has acquired a spin lock, the other processes keep on spinning. So again, this is not time, resource, and power efficient. But at least if the critical section is small, spin locks are a good idea. But if you have the spin lock and then you get preempted, then it's a major issue. The reason being that all other processes that are waiting on the spin lock may have to wait for a long time. So locking as such prevents kernel data structures from corruption, but it brings along a set of problems as well, as we have discussed, for real-time operating systems. So the standard idea of a spin lock is that before acquiring a shared resource, you acquire the lock and then you release. And let's say if another thread comes in, so let's say T1 has acquired the resource and T1 and T2 comes in. Well, T2 will just keep on checking the lock to see if it is free or not in a loop. So this is why it's called a spin lock or a busy wait loop. Where let's say if you're given a certain memory address, let's say if you set it to 1, the lock is taken, otherwise it is not taken. So in this case, all that you do is that after the lock has been set to 1, you check if the lock is equal to 0 and you just do this repeatedly. So this repeated checking is known as a spin lock. So what is so special about Linux and why do most real-time offerings actually target Linux? In the sense, either create an extra layer on Linux or an extra module for Linux. So why do we do that? Well, so we have discussed this at length in previous chapters as well. But a key reason is that the source code is freely available. It is robust and reliable. It is modular, configurable. So Linux is quite modular in the sense it supports kernel modules that can be loaded on demand. A lot of configurability options via the kernel compilation menu as well as later on at runtime as well. And it's quite scalable. So starting from servers to small devices, it runs everywhere. Great support for networking and the internet. Runtime licenses are not required. And there is a very large pool of developers, people who know and understand the Linux kernel code base. So going back to the early days of Linux in 2004, when a survey was done among a lot of developers and users, as to what was exactly inhibiting the adoption of Linux in real-time applications. The major issue, other than things of lack of software support, environment support, and so on, was the real-time limitations of the kernel. So most of the people said that the kernel is still too general purpose; it is not real-time ready. So the first culprit was interrupt handlers, right? So what happens is that Linux has an interrupt request queue. That's a subsystem, and its latency is quite unbounded. So what happens is that the task preemption latency will increase with the hardware interrupt load because you really don't know how long an interrupt will take to process. So as a result, if you're trying to preempt a task, then the latency might be quite high because once a task has been preempted, the kernel runs and the kernel may have a lot of interrupt related work. So may just do that. Interrupt handlers themselves are not preemptable. This further causes issues. And again, we don't have a priority system for interrupts. This is something that is required because you may have extremely low priority interrupts, which is fine if we handle several hours or even several days later. But we don't have that. So as a result, the IRQ subsystem of Linux will always treat interrupts as high priority and preempt tasks unconditionally, which is not really good for real-time tasks, right? So this is not advantageous at all. In fact, it is quite disadvantageous for real-time tasks. So because we have this problem, and along with that, as I have discussed earlier, Linux interrupts are divided into two parts. So it's the same for most of the other operating systems as well. We have a top half and we have a bottom half. So the top half is a part that needs to be done immediately, and the bottom half can be scheduled later. So this is known as the soft IRQ mechanism in Linux. But modern Linux has other things such as work queues and tasks and so on. But the key point is that even these bottom half handlers don't come with real-time guarantees of exactly how long they are going to execute on a CPU, right? So this guarantee is something that they do not have. So these bottom halves are of course activated by a primary interrupt such as the timer or the disk or network. But then the bottom halves, the soft IRQs, get queued in a queue and of course run later. And that is when they can, mind you, they're still running with kernel priorities because both of these are kernel tasks. And that is where they can take up the resources of real time tasks and delay them. Culprit 2 is basically dealing with locks. So the primary problem, as we have discussed, is a spin lock by nature is not preemptable because if you preempt a spin lock, then what will happen is all the processes that are waiting. So I want to revise that. If you preempt a process that is holding a spin lock, right, and let's say something else executes, all the processes that are waiting on the lock will not be able to make progress. Why? Because the original process which was supposed to release it is not running. So because we don't have priority inheritance in Linux, at least in this space, this causes an issue and a somewhat significant issue. Because the kernel has a lot of critical sections. And if, let's say, while holding a lock, the kernel is preempted, it will cause a lot of problems in terms of tasks missing their deadlines. This is exactly why in the top halves of the interrupt handlers, critical sections are not allowed, right? Otherwise, what will happen is they may just keep on waiting forever, and this is not something that is allowed. Furthermore, it is important to do very exhaustive kernel level testing to identify the worst case code paths or the code paths with the maximum amount of delay. We're looking at if I have this lock, I get preempted, what happens to the others, and so on, such that critical sections can be written in a better way, right, using as few locks as possible. This is quite hard, it's quite labor intensive to clean up all of these critical sections. But this is again, along with the previous issue of interrupt handlers, locking is a major issue in modern operating systems. So if you look at the development of locking per se in the Linux kernel, so of course now we are at kernel version 5, I'm only looking at the early history. So we started with an absolutely non-preemptable kernel. So kernel gradually became preemptable outside critical sections, as you can see, but critical sections still had spin locks. Then the schedulers improved, and finally we had real-time variants of Linux where kernel level critical sections also became preemptable. Interrupts got prioritized, priority inheritance protocols came in, and the timers became far more high resolution. So we are moving in that direction. Linux as of today, so there is a version of Linux known as Zephyr. So Zephyr is a reasonably real-time version of Linux, which has many of these interesting features in it. Other issues that may deter a user from using Linux, other than the real-time nature, is that unlike Windows, Linux is not all that popular. So there are issues with standards, device drivers, and qualification testing. But again, these were problems that were more prevalent with Linux like operating systems maybe 10 or 20 years ago. As of today, things are much better, much, much better. So to make Linux real time, the main idea is we target both interrupts and preemption, right? So these are the two culprits that we had identified. So both need to be targeted. We need to make interrupts better and clearly make the kernel more preemptible. So the approach one, the first approach, is to improve the Linux kernel itself, which basically means to re-architect the Linux kernel such that every call, be it an interrupt, a system call, has a bounded latency. And furthermore, any approach taken by the mainline Linux kernel has to ensure that it remains preemptible with a bounded latency all the time. So interesting forks have come out of the kernel project tree, such as Linux RT, the Preempt RT project, Monte Vista, and so on, where you realize that the complexity of improving the kernel is quite high. So it's much better to fork the design and create a real-time Linux, which is fine. The other is kind of to write a virtualization layer below the kernel, right? Between the, if this is the kernel, this is the hardware. We would like to add a virtualization layer over here below the kernel. It will handle all the real-time requirements, right? Such that, the even if you don't modify the kernel, the system will still appear to be real time to an outside observer. So many such projects, which are primarily happening at the hypervisor level, or some layer which is at the lowest layer of the kernel, are getting quite popular. So RT Linux used to be a very popular idea in this space. So it is not, it's kind of decommissioned now. But the RTAI and Xeno projects and the Xenomai projects, these are still alive in some or other form, where the main idea is to add a layer below the Linux kernel. So the kernel latency would look like this if I were to, break it down into all the components. That assume there is an interrupt and there is a waiting task. So the interrupt will have an interrupt latency. Then the interrupt handler will run. That's the handler's duration. Then the original task or some other task will be made runnable. So the scheduler will take some time to figure out which task to schedule. Then the scheduler will, this is the time to actually invoke the scheduler, and this is the time that is the scheduler running time. And finally, the task will run. So basically, this entire period of the interrupt latency, handler duration, scheduler latency, and the scheduler duration, in a sense, comprises the kernel latency for an interrupt. So this basically means that we have to reduce the time it takes to process the interrupt as well as invoke the scheduler. The shorter is this time, the more responsive is the program. So what are the sources of interrupt latency, right? So we have already discussed spin locks in the past. So there are several variants of spin locks, but let's look at one that is commonly used. So the main idea is to prevent concurrent accesses between the process context and either other processes or interrupts. Right? So you don't want too much of collision in a lock. Otherwise, what will happen is that if, let's say, one process with a spin lock is preempted, a lot of processes will just wait on it and they will also not make any progress. So, of course, critical sections have to be protected by locks. And as I say, if the critical section is small, then a spin lock is a good idea, right? But the point is that if the interrupt handler is also trying to access a critical section, that will cause delays because the duration of the critical section can be large. This is why a very wise decision was taken while designing the Linux kernel. The top half will not access any critical section, right? So it will not do that because this part is very, very performance sensitive. So if it starts accessing critical sections, its performance may dip. And also, developers found out that even if it doesn't access a critical section, it's not a big deal. So this is why it is very important to actually protect spin locks and also understand that if tasks that are holding on to spin locks, if they get preempted, then the rest of the tasks will have to wait for a long time, may have to wait for a long time. So coming to the top half and bottom half part, in the top half, what we typically do is we don't allow it to access critical sections and we also disable interrupts. So this ensures that the entire top half executes atomically, right? So nobody is there to interrupt it in the middle. And because it does not access critical sections, right? It does not have critical sections. It will really not be the case that both interrupts are disabled and it is waiting on some sort of a spin lock to release. So that's not going to happen. So this correctness problem is, so this is important, right? Because if the top half is, if you're disabling interrupts and you're accessing critical sections at the same time, this is quite problematic. Because assume interrupts are disabled and then a top half tries to access a critical section and it waits. It may have to wait for a very long time and nobody else can preempt it. The bottom half, on the other hand, is scheduled by the top half. It runs at a later instant of time and it does a bulk of the interrupt processing. So, definitely for real time critical interrupts, the bottom half should not be used because it may be scheduled much later, right? And it will also depend upon other interrupts of the system. So it is always best for a real-time critical interrupt to keep its footprint as small as possible and preferably execute all of it in the top half to reduce the interrupt latency. How far this is possible and practical, that is a separate issue. But this is something that is very, very application dependent upon the programs, the workloads, and the interrupt. Furthermore, what Linux needs to do, it does to a certain extent, but it can do more, is that interrupt handlers at the moment are executed directly by the CPU interrupt mechanisms. In the sense, an interrupt comes to the CPU, it looks up an interrupt table and invokes it. This is not really under the control of the Linux scheduler. As a result, interrupt handlers, as you can see, they have the highest priority and they can swap out. They can force a context switch for any existing high priority real time task. If you want to design a genuine or a pure real-time operating system, this behavior has to be disallowed. And we'll have to allow all interrupts to be under the control of either software or some programmable hardware, right? Either software or some kind of a programmable hardware. Now, coming to improvement of preemption, of course, the Linux kernel code is modified. So you want to minimize the amount of time that the kernel is spending in the non-preemptable parts of the code. The primary strategy is to reduce the length of the non-preemptable code, but this is easier said than done. To allow for very flexible preemption, the code does become complex, and this is again a problem with real time operating systems. But again, with careful design and with a lot of research, it is possible to design parts of the OS code such that the amount of non preemptible sections are absolutely minimal. Then let's come to interrupts. So, one key idea that we have seen is that look, the Linux kernel interrupt architecture is quite inflexible. Furthermore, what we have done is that the top halves run by disabling interrupts, and to ensure that they don't shoot themselves in the feet, we mandate that they will not access any critical sections. But is that enough? Well, clearly no. The entire kernel has to be made preemptible. And to do that, what we can do is we can follow the approach of Xenomai and RTAI, which is the small layer which is below the kernel. So what this can do is that this can intercept and manage all the hardware interrupts. So the hardware will basically deliver the interrupts. So this micro thin virtual machine. This virtual machine will then control the interrupts, enforce a priority, right? And then have a real-time scheduler for which the kernel is one of the applications. So the kernel itself will now run as a low priority task as opposed to earlier days when it was a high priority task, because now the highest priority is basically the virtual machine, right, or the hypervisor. Same thing, virtual machine manager and hypervisor are considered the same. So in this case, you're adding a thin virtual layer on top of hardware to essentially take care of all interrupts, which means receive them from the CPU, receive notifications about them from the CPU, run the handlers, and maybe deliver some interrupts to the kernel and run the kernel as and when necessary. So you can also think about a very generic hypervisor which can run other interrupt handlers or other system management tasks in parallel with the kernel. So coming to the interrupt abstraction model, in this case we don't modify the Linux kernel as opposed to the previous case where we were adding preemptibility. So the Linux kernel per se runs unmodified. We have these thin layers which either could be a virtual machine below the kernel, that is option one, or the other is that we could load these loadable modules in the kernel which are basically real-time tasks and APIs which fundamentally change the behavior of the kernel in the sense that they remap the interrupt tables, they enforce a priority of interrupts, decide what to do with each interrupt. So this entire policy, if the kernel does allow, can be coded into a loadable module and loaded at runtime. What are the limitations of this interrupt abstraction model? So we need to understand real-time applications are becoming more and more complex. There is a need to build complex applications which also have virtual memory. So we have always indicated that virtual memory is a cause for low performance. Of course, it is required. Nobody is denying the fact that virtual memory is not required. But virtual memory comes with its own set of problems. Effective resource management, this would require at least the implementation of PCP like protocols on Linux. And furthermore, for process isolation, that becomes a problem if you don't have virtual memory. So we'll then have to have some other mechanism, again, something either similar to virtual memory or similar to a hypervisor, a regular virtual machine monitor, to ensure that we have proper process isolation. So coming to the most popular RTOSs as of 2021, 2022, well, these are the ones. So let me go from bottom up. So I was talking about Zephyr, which is a part of the Linux Foundation's offerings. VxWorks is something very popular, initially designed by WinRiver. So we have discussed this in different lectures in several different contexts. Then we have the microcontroller OS. something by Microsoft Express Logic. Pike OS is something we have discussed, and Neutrino was being used by BlackBerry phones, not used to that extent this much. Nucleus is a Mentor Graphics product, same as MQX. Lynx OS is again very popular. In fact, this list has been taken from the website of Lynx OS. Keel is becoming very popular mainly because it runs on ARM. And as you know, ARM is a market leader for the IPs of all small embedded systems. So that's the reason Keel RTX is something that has been receiving a lot of attention these days. Integrity is also a nice product, and what I personally use for course assignments is free RTOS, which is an Amazon product. So free RTOS comes with an MIT license. It has a lot of add-on support and libraries can be used. Embedded OS is also something which is very popular uh, in this list. So as you can see, there are some extremely popular offerings, and viewers of this video are more than welcome to download some of these operating systems and run them. So this brings us to an end of this chapter. So we'll continue looking at different aspects and facets of real-time operating systems. But if I would conclude, my concluding remarks would be like this, that point number one, preemptability of the kernel is important. So you want to minimize the amount of time that your kernel is in a non-preemptable mode. Furthermore, if this is combined with locking, so the moment you're hanging on to a lock and you get preempted, that's actually a terrible problem both for you as a thread and for other threads which are waiting on you. And most spin locks have this problem. So that is the reason we need a notion of priority inheritance, right? Then, of course, managing interrupts is a problem. Well, traditionally, interrupt top halves have always disabled interrupts, so that causes preemptability problems. Even in systems that have large, bottom halves, which are scheduled later, these bottom halves can cause a fair amount of uh, performance issues. The reason being that they are scheduled much later, so that increases the interrupt response time. And when they are scheduled, they may hold up the CPU for a long time. So it is important to look at all of these issues together and propose a solution, so which is exactly what real-time operating systems do, which is by making the kernel code extremely preemptible, using approaches that don't rely that much on locking. So there are a class of algorithms known as lock-free algorithms, which don't have this problem. And of course, then adding hardware support for managing interrupts better, interrupt priorities, and so on. So again, this lecture will end here, right? This is kind of my second farewell for this lecture. So the next lecture will again look at other aspects of other real-time operating systems.